Good evening, students. Welcome to day 15 POC-II crash course. Thank you so much for joining. So in today's session, this will be the last session, and in today's session, I'll be discussing about chemistry of phenanthrene. And at the end of this session, I'll be covering few important, most expected 2 marks questions also. That is diphenylmethane and triphenylmethane structure and uses. Now, in yesterday's session, I have discussed about chemistry of anthracene. So, if you have missed yesterday's session, then a replay will be available. You can watch it on my YouTube channel. So, during the session, if you have any doubts related to this topic, today's topic, then you can type your questions in the live chat. Alternatively, if you are watching the replay of this particular session, then a WhatsApp group link will be available in the description of this replay. Okay, you can join in that WhatsApp group and you can post your doubts so that I will answer your doubts from time to time. And even for the previous videos also, if you have not attended the regular sessions, but if you are watching any replay, then a WhatsApp group link will be available in all those videos description. You can join in that WhatsApp group and you can clarify your doubts. And soon after this session, today also quiz will be enabled based on the chemistry of phenanthrene. That is today's topic, whatever I am going to discuss. Okay. So review the concept for about 10 to 15 minutes. As soon as this session is completed, then only attempt the quiz. Now, without wasting much of your time, let's get into today's topic. So first, I'll be discussing about resonance phenomena in phenanthrene. So this resonance phenomena in phenanthrene is very much similar to anthracene, and there will be few exceptions also. Now let us discuss all those things. So this is the structure of phenanthrene, students. So if you look at this particular structure, it is very much similar to anthracene. So when it comes to anthracene, anthracene consists of 3 aromatic ring systems which are fused linearly, or this is called ortho fusion. When it comes to phenanthrene, it also consists of 3 aromatic ring systems. Okay, but all these 3 aromatic ring systems are fused angularly. If you see the first and second ring with certain angle, they are fused, and similarly 2 and 3 rings with certain angle, they have fused. Okay, so this type of fusion is known as angular fusion. The molecular formula of both these compounds are similar, that is C14H10 only. Okay, even phenanthrene, the major reservoir, that is the major source, is coal tar only. Synthetically, it can be prepared by different methods, which I will be explaining in the next coming sections. Phenanthrene is considered as an isomer of anthracene because the phenanthrene molecular formula is also same as that of anthracene. The difference is in anthracene, all the 3 aromatic ring systems are fused linearly. When it comes to phenanthrene, these 3 aromatic rings are fused angularly. That is the only difference between both anthracene and phenanthrene. That is why phenanthrene is considered as an isomer of anthracene. Now coming to the number of resonance structures, as we are aware, the formula is n+1, where n is the number of rings. So the total number of rings present in the structure of phenanthrene is 3. So 3 plus 1, 4 resonance structures are supposed to be formed for phenanthrene. So this number is same as that of the anthracene. But when it comes to the resonance structures of phenanthrene, 5 resonance structures are possible. Okay, so here that means extra resonance structures are possible when it comes to the phenanthrene. Okay, so it is because of the greater stability of this particular molecule when compared with anthracene. So this is itself indicates. So both anthracene and phenanthrene are having 3 aromatic ring systems only. So as per the thumb rule, n+1 means 4 resonance structures should be possible even for the phenanthrene. Okay, similar to that of anthracene. But when it comes to the original resonance structures possible for phenanthrene, it is 5. Okay, that means 1 extra structure is possible for the phenanthrene. So greater the number of resonance structures, greater will be the stability. So based on this also, we can easily make out that even though phenanthrene is an isomer of anthracene, yet it is more stable when compared with anthracene. Now let us see, these are the 5 resonance structures of the phenanthrene. Now let me explain how we can draw these 5 resonance structures. Let us first talk about the first resonance structure. So to make first resonance structure, first give the carbon skeleton of 3 rings. Okay, fusion of the 3 rings. Okay, so I will give you one particular notation how you can draw the or learn the phenanthrene structure. So this is how you can learn easily the phenanthrene structure, students. So first write 2 hexagon ring systems, okay, and connect these 2 hexagon ring systems like this. Okay, so first I am making only the carbon skeleton. Okay, now join these 2 hexagon ring systems like this. Join these 2 hexagon ring systems like this. So this is very easy representation of the phenanthrene ring system. Now try to adjust the double bonds. Okay. The first resonance structures write such that all the aromatic ring systems will be getting 3 alternative double bonds. Okay. So in that way, make the first resonance structure. Okay. So how we can get, when we draw like this, then only 3 double bonds are possible in each in each aromatic ring system. Okay. So this is how we can make the first resonance structure. So from first resonance structure, we can draw second resonance structure. So when it comes to the anthracene, I hope you remember how we modified the resonance structure. So after writing the first resonance structure, we have modified only first aromatic ring. When it comes to the anthracene, we have modified only first aromatic ring, so that from first structure, we can write the second resonance structure. Okay. Now to write the third resonance structure from second, we have modified the double bonds position in second aromatic rings. Okay. By keeping the first and third rings double bond position same. Now from third, we have written fourth resonance structure by modifying the double bond position in the third aromatic rings. Okay, by keeping 1 and 2 same as that of the third resonance structure. So this is how we have followed this particular order. That is, first you make change in the first aromatic ring, then second aromatic ring, then third. Okay, so like that, if you remember, it becomes very easy for you to write the resonance structures and remember the resonance structures. Okay. So in similar lines, now if you consider for phenanthrene resonance structures, how we can make the second resonance structure from 1. If you see, let us label these aromatic rings as 1, 2, 3. Okay. So what I have told, first resonance structure, give all benzene rings. Okay. This is the first resonance structure done. Okay. Now to write the subsequent resonance structure, change the double bond position in this order. That means in order to write the second resonance structure, okay, change the double bond position in the only third aromatic rings. Okay. Keep the other 2 aromatic rings same as that of the first resonance structure. Okay. You can see here, first ring, second ring, second ring. In both the structures, the double bond position is same. Okay. Where the actual change is happening in the third ring system. Okay. In the third ring system of first and second resonance structures, if you see here, we have represented 2 different Kekulé structures. Okay. Just a double bond position is changed to the adjacent position. That is how the other Kekulé structure we have drawn. Okay. Now to write the third resonance structure from second, what is the change that we have to make is only we have to modify the double bond position in the first aromatic ring system. Okay. Now consider the second resonance structure. Just to change the double bond positions with respect to the first aromatic rings to the adjacent position, so that we get like this. Okay. Keep the double bonds in case of second and third aromatic ring system same as that of the third resonance structure. We are not disturbing the second and third rings. Okay. That means where is the change that we are making? In order to write the third aromatic ring system, make the changes only in the first aromatic ring system. Remaining 2 aromatic rings double bond position will be kept as it is. Now to write the fourth resonance structure from third, what we have to do is again change the third aromatic ring system's double bond position. Okay, so this is the third aromatic ring. Okay, so write the double bond positions in case of first and 2 ring system same. Okay, so you can observe these 1, 2 rings in third structure and 1, 2 rings in fourth structure are kept similarly. Okay. Now, when it comes to the double bond position in third ring, okay, so third ring in case of third resonance structure, just shift to the adjacent positions. Okay, so in that way, you can write the other Kekulé structure for the third aromatic benzene ring system. Okay, that means the difference between the fourth and third resonance structures is they differ only in terms of the double bond positions with respect to third aromatic ring. Remaining structure is same. To write the fifth one, okay, we have to consider the first structure. I have written here as 1-2, or you can write it as 1.2 also. This is the simple abbreviation which I am giving here so that you can easily remember and reproduce without any mistakes in the examination. Okay, so 1-2 or 1.2 you can consider. That means take first resonance structure. Okay, consider first resonance structure. Modify second ring of the first. Okay, this is the second ring. Means write the first resonance structure as it is first. That means 1 and 3 rings double bond position will be similar. Okay. Change only the second aromatic ring double bond position. Okay. So here in the first structure, shift to the adjacent position. The double bonds shift to the adjacent position so that you can write the another Kekulé structure for the benzene ring, second benzene ring. Okay. So this is how you can draw fifth resonance structure from first. So that is why I have written here 1-2. That means for writing fifth resonance structure, consider first resonance structure, modify only second ring. Okay, so in the earlier resonance structures, what we have drawn third from second. We have drawn fourth from third. Okay, that means the subsequent changes we are doing. Okay, but when it comes to the fifth resonance structure, consider first resonance structure, modify only the second aromatic ring. So that I have represented as 1-2. So this is the sequence that you can follow, students. First, write the first resonance structure. Make sure that all aromatic rings are benzonoid rings. Okay. Now, in order to write the second resonance structure, consider first structure, okay, but change the double bond position only with respect to the third aromatic ring, okay, of the first resonance structure, so that you can make the second resonance structure. Now, in order to get the third resonance structure from second, take the second structure as it is, modify only the first aromatic ring double bond positions. Okay. Now, in order to write the fourth resonance structure from third, take the third resonance structure as it is, but modify only the third aromatic ring double bond position. Now, to write the fifth resonance structure, take first resonance structure. Okay. Write the structure as it is, modify the double bond positions with respect to the second aromatic ring. Remaining structure should be drawn similarly. Okay, so this is how subsequently you can change the position of double bond. Okay, so that you will get the next resonance structure. So that in fact the definition of resonance structure is that only. No, that means the resonance structures will differ only in terms of the delocalization of electrons. Simply the double bond position will be changed. So when it comes to the examination, students, you have to represent only like this. Okay, this is for your remembrance purpose. This simple trick I have given here. Okay, you cannot write this thing. Okay, when it comes to the examinations. Now, the resonance hybrid of phenanthrene can be represented like this. Okay, so first write the carbon skeleton, and because all the 14 carbons in phenanthrene are now having double bond character, that is what we can understand from these 5 resonance structures. Okay, so keep circle which covers all the 6 carbons in each benzene ring system, and that is how we can draw the resonance hybrid of the phenanthrene. So let us consider now Fry's rule and the stability of these resonance structures even in case of phenanthrene also. So in order to understand which of these resonance structure is highly stable among 5 resonance structures of phenanthrene, first we have to label these aromatic rings as benzonoid ring systems and quinonoid ring systems. Okay. So if you look at the first resonance structure, each of these rings are benzene rings only. That is why we have labeled as with small b, which means benzonoid ring systems. Now when it comes to the second resonance structure also, label each ring as benzonoid or quinonoid depending on the number of double bonds. Okay. So the first ring is having 3 double bonds, so it is benzonoid. Third ring is also having 3 double bonds, so it is also benzonoid. Now the middle ring is having only 2 rings, so we label it as quinonoid. Okay. Similarly, label all other resonance structures also. Third is having 2 benzonoid ring systems and 1 quinonoid. Fourth is also having 2 benzonoid and 1 quinonoid. Now coming to the 5, it is having 2 quinonoid, okay, rings and only 1 benzonoid rings. So from these structures, you can easily make out that the one which is having more benzonoid ring systems is highly stable according to the Fry's rule. So among these 5 resonance structures of phenanthrene, first resonance structure is highly stable because it is having 3 benzonoid ring systems. Okay, and also you can easily make out from these resonance structures that the 5th resonance structure is having least stability because it is having more number of quinonoid rings and very less number of benzonoid rings. Okay, so 1 is the highly stable resonance structure and the 5th resonance structure is the one which is having the least stability. Now let us consider the stability of phenanthrene when compared with benzene or other polynuclear aromatic hydrocarbons. So if the structures of all these compounds are given, benzene, naphthalene, anthracene and phenanthrene. So the resonance energy of all these compounds are given in this particular line. So benzene resonance energy is 150.6 kilojoules per mole. Now when it comes to phenanthrene, it is 385 kilojoules per mole. Okay, and the number of rings present in all these compounds, aromatic compounds are given. Benzene is having 1 aromatic ring, naphthalene is having 2 aromatic rings, phenanthrene and anthracene are having 3 aromatic rings. Okay, so as we have discussed in the earlier course videos of naphthalene and anthracene, here for phenanthrene also we have to consider the resonance energy with respect to each benzene ring. Okay, the resonance energy whichever is mentioned here is corresponding to the 3 aromatic rings. Okay, so when we calculate this for with respect to each benzene ring, we have to divide this value, that is 385, with 3. Okay, then we will be getting 128.3 kilojoules per mole as the resonance energy of phenanthrene with respect to each benzene ring. Okay, so this value, if you see, it is less than that of the benzene resonance energy, which is also having one aromatic ring system. Okay, now the relationship between the aromaticity and resonance energy is that aromaticity is proportional to the resonance energy. Okay, that means greater the resonance energy, greater will be the aromaticity, greater will be the stability, and lesser will be the reactivity. Okay, so based on this, we can easily say that phenanthrene is less aromatic than benzene. Okay, so lesser the aromaticity, lesser will be the stability. That means more or greater will be the reactivity. Hence, phenanthrene is more reactive than benzene. So for overall, for all these molecules, the stability order, if you see, benzene is highly stable among all these 4 compounds. It is because it is having greater resonance energy. Next comes naphthalene, and then phenanthrene, and then finally anthracene. Okay, so you can here also easily make out the statement which I have mentioned earlier. Phenanthrene is stable than anthracene. Okay, both these compounds are having 3 aromatic ring systems only, but the resonance energy of phenanthrene is more when compared with anthracene. Okay, and the same is even evidenced in terms of its resonance structures. Okay, phenanthrene shows 5 resonance structures. When it comes to the anthracene, it is having only 4 resonance structures. So greater the number of resonance structures, greater will be the stability. Okay, and also greater the resonance energy, greater will be the stability. Greater the stability means it is greater aromatic. Okay, so in that way also we can relate easily. I hope the resonance phenomena in phenanthrene is clear to you, students. So as you have seen, even though anthracene and phenanthrene both are having 3 aromatic benzenoid ring systems, yet phenanthrene is having more number of resonance structures. Okay, as per the formula, 3 plus 1, only 4 resonance structures are supposed to be existing even for the phenanthrene, but it is having 5 resonance structures. So this itself indicates greater the number of resonance structures, greater will be the stability. So this itself indicates that phenanthrene is more stable when compared with anthracene. So if you have any doubts related to the resonance phenomena in phenanthrene, you can type your questions in the chat. So meanwhile, I'll begin with the next topic, that is isomerism phenomena in phenanthrene. So if the structure of phenanthrene along with numbering is given, students. In case of naphthalene and anthracene, we have considered 2 different structures here when it comes to the isomerism phenomena. So one structure of anthracene or naphthalene is given in terms of the numerical values, while the other structure is given in terms of the different positions, that is alpha beta designation in case of naphthalene, alpha beta gamma designation when it comes to the anthracene. When it comes to phenanthrene, the carbon atoms are designated with numbers. It is because the number of different environments in phenanthrene are more. Okay. Now let us consider, let us label these ring systems as 1, 2, 3 ring systems. Here, the first and third aromatic rings are having isomeric property. So you can consider them as numbering that is same as that of the naphthalene ring system. Okay. So here, the first number we start from here, 1, 2, 3. Now once we complete fourth, we don't give numbering to the second aromatic ring systems, because second aromatic ring system is the junctional aromatic ring which is present between 1 and 3. Okay, the carbon atoms which are present in the second aromatic ring are in sharing with the first and third aromatic ring. That is why first we always give numbering to the isolated ring systems first. So after completing 4 in the first aromatic ring, then the numbering will be continued for the third aromatic ring system, that is 5, 6, 7, 8. Now once both these 1, 3 rings are completed, now whatever the remaining carbons are there, we will give numbering to them. That is, we will give numbering to second aromatic rings. That is, the 2 carbons are labeled as 9 and 10 carbon atoms. So this is how numbering will be given when it comes to the phenanthrene. So from the structure of phenanthrene along with its numbers, you can easily make out that first and third aromatic rings are having isomeric property. So in that way, so the first carbon and 8th carbons are chemically equivalent. Okay. Second and 7th carbons are equivalent. So carbons are equivalent and means the hydrogens which are present at that position are also equivalent. Okay. Similarly, the hydrogens which are present at third and 6th positions are equivalent, and the 4th and 5th hydrogens are also chemically equivalent. Okay, so here 4 different positions are there. Okay, now coming to the second aromatic ring systems, position 9 and position 10, they are chemically equivalent. That means the hydrogens which are present at 9 and 10 positions are identical. Okay, that means overall if you see in case of phenanthrene, 5 different positions are there. Okay, that means out of the 10 hydrogens that are present in phenanthrene, they belongs to 5 different types. Okay, so in that way overall 5 different positions are there. So 1 and 8 are identical, 2 and 7 are identical, 3 and 6 are identical, and 4 and 5 are identical. Like this you can, like this. Okay, and finally 9 and 10 are identical. So total 5 different positions are there in the structure of phenanthrene. Okay, so you can remember like this. So when we conduct electrophilic substitution reactions for phenanthrene, the incoming electrophile, it prefers to attack at any of these 5 possible positions. That is why there is probability of formation of 5 different monosubstituted phenanthrene derivatives when we conduct electrophilic substitution reaction. Okay, and they are designated as 1 isomer, 2 isomer, 3 isomer, and 4 isomer. And then when attack occurs at 9th position, that is known as 9 isomer. That is 9 substituted phenanthrene derivative. So this is how we will label the resulting derivatives. That means under electrophilic substitution reactions of phenanthrene, now in the next coming chapters, we will discuss about 5 types of attacks. Okay, 1, 2, 3, 4, and then 9th attack. Okay. We have discussed 3 types of attacks when it comes to the anthracene. 1, 2, and 9. 9 is nothing but the gamma attack. Okay, so like that when it comes to phenanthrene, we'll be discussing 5 different attacks. I hope the isomerism phenomena in phenanthrene is clear to you, students. So when compared with anthracene, in anthracene only 3 different types of hydrogens are there. But when it comes to phenanthrene, it consists of 5 different hydrogens. Okay, and hence 5 different positions are there. So the same positions we will be try to attack the electrophile when it comes to the electrophilic substitution reactions. So if you have any doubts related to this topic, that is isomerism in phenanthrene, you can type your questions in the chat. So the next topic which I am going to take is the Haworth synthesis. So here I am not covering multiple number of synthesis, students. You might have learned. So I have discussed multiple number of synthetic routes for naphthalene and anthracene, in which one of the most important synthesis is Haworth synthesis. Okay. Now let us consider the Haworth synthesis of phenanthrene. Now let us consider the Haworth synthesis of phenanthrene. So meanwhile, if you have any doubts related to the earlier topics, you can post your doubts in the chat. Haworth synthesis of phenanthrene can be written in similar way as that of the previous polynuclear aromatic hydrocarbons which you learned, that is naphthalene and anthracene. Now in case of naphthalene, the first step involves reaction between benzene and succinic anhydride. Okay. When it comes to the anthracene, the first step is the Friedel-Crafts acylation reaction between the benzene and phthalic anhydride. Okay. Now when it comes to the phenanthrene, because phenanthrene consists of 3 aromatic ring systems, okay, that means you can consider this particular structure as a naphthalene. Okay. Now naphthalene ring is attached to the another benzenoid ring systems with angular fusion. Okay, you can consider like that. Now in that case, we can consider naphthalene as one of the starting compound. That means in the place of benzene, okay, when it comes to the naphthalene and anthracene, we have taken benzene, no? So in the place of benzene, we can take now naphthalene as one of the reactant. Okay. Now when naphthalene structure is already present, we need only one more ring system. Now this one more ring, benzenoid ring system, we can obtain from is anhydride, which is having only one ring system. That means we can take here succinic anhydride similar to naphthalene. So in this way, the first step in Haworth synthesis of phenanthrene is the Friedel-Crafts acylation reaction of naphthalene with succinic anhydride in the presence of aluminum trichloride. So the first step involved in the Haworth synthesis of phenanthrene is the Friedel-Crafts acylation reaction of naphthalene with succinic anhydride in the presence of aluminum trichloride. During this reaction, the succinic anhydride undergoes cleavage between carbon and oxygen bond, and this carbonyl functionality gets attached to the first position on the naphthalene ring system. Because in the electrophilic substitution reactions of naphthalene, the preferred point of attack of electrophile is at first position. So write the structure of naphthalene first. So this is the structure of naphthalene. Okay. And this is the first position on the structure of naphthalene. So attach this carbonyl group. Okay. This is the carbonyl group to the first position. Okay. Now this carbonyl group is attached to a 2 carbon chain. So these are the 2 carbons attached to the carbonyl group. Okay. Now these 2 carbons are again this side attached to the COO group. Okay. Now during this cleavage, this COO group gets converted to COOH. That is why we have written there COOH. So this is how we will be getting the corresponding intermediate. Now this CO group is not required in the final structure of phenanthrene. That is why the CO, that is carbonyl group, is converted to CH2 group by subjecting it for Clemmensen reduction in the presence of zinc amalgam and hydrochloric acid. Okay, and that is how we will be getting the next intermediate. Now this intermediate, even carboxylic group is not needed. So we have to get a cyclic ring system at this particular position so that we get this part of the phenanthrene. Okay, that means cyclization has to be occurred, and before that the OH group should be removed. That is why dehydration is performed here by treating the resulting intermediate with concentrated sulfuric acid. During this dehydration, the hydrogen of this aromatic ring system and the OH group from the carboxylic group will be removed in the form of water molecule. Okay, and that is how upon dehydration, this carbonyl group gets attached to the aromatic ring system. And that is how this new bond is formed. And that is how cyclization occurs between this naphthalene ring system with that of this 6-membered ring system. Okay. Now, in order to get the final structure of phenanthrene, even this carbonyl group has to be removed. Okay. So, to convert this carbonyl group to CH2 group, here Clemmensen reduction will be performed in the presence of zinc amalgam and hydrochloric acid. Okay. And that is how we will be getting tetrahydrophenanthrene. Now, the structural difference between tetrahydrophenanthrene and phenanthrene is that it is lacking 2 more double bonds. These 2 double bonds are required. Okay. In order to incorporate 2 double bonds, hydrogens present at these 4 positions has to be removed. And that is why tetrahydrophenanthrene is subjected for dehydrogenation by heating with selenium. Then these 4 hydrogens will be removed, and that is how 2 double bonds will be incorporated. Okay. And finally, we get phenanthrene, that is the corresponding product. So this is how the Haworth synthesis of phenanthrene involves. The first step is Friedel-Crafts acylation reaction, second step Clemmensen reduction, third step dehydration, fourth step again Clemmensen reduction, and fifth step is dehydrogenation. Okay, so if you look at this particular flow, students, this is very much similar to the 5 steps which are involved in the Haworth synthesis of naphthalene. Now, if you feel difficulty in remembering and writing all these 5 steps, you can mention the Haworth synthesis of phenanthrene like a single step reaction also. Write only the first step. That is, first step is the Friedel-Crafts acylation reaction between naphthalene and succinic anhydride. Give aluminum trichloride and keep these multiple number of arrows, which indicates that it is a multi-step reaction. Okay, and directly write the structure of phenanthrene. So in this way also, in single step also, you can write the Haworth synthesis. I hope the Haworth synthesis of phenanthrene is clear to you, students, because here phenanthrene consists of angular fusion of 3 aromatic ring systems. The starting compounds would be naphthalene and succinic anhydride. Okay, so that is how there will be difference in the starting compounds when compared with naphthalene or anthracene, but otherwise the flow remains, it is the same when compared with the previous polynuclear aromatic hydrocarbons. So if you have any doubts related to Haworth synthesis, you can type your questions in the chat. And the next topic which I am going to discuss is the most important one, that is the reactions of phenanthrene. So even phenanthrene, it will undergo similar reactions as that of the naphthalene and anthracene. So first, let me discuss about the electrophilic substitution reactions. So let me quickly share my screen. Meanwhile, if you have any doubts, you can type in the chat. Now let us first consider the overall reactions of phenanthrene. So similar to anthracene and naphthalene, phenanthrene also undergoes electrophilic substitution reactions, addition reactions, oxidation and reduction reactions. Now in this particular course video, first let us consider the electrophilic substitution reactions. Now, if you look at the structure of phenanthrene, it consists of 10 hydrogens, which belongs to 5 different classes. Okay, so here also, whatever the discussion that I have made for naphthalene and anthracene, in a similar way, you have to explain even for the phenanthrene. Okay, that is why electrophilic substitution occurs and also why only substitution is preferred. So, it is similar to that of anthracene. So, this phenanthrene also consists of 7 alternative bonds, that is 7 conjugated pi bonds. Okay, and that is how it is considered as electron-rich molecule. And these electron-rich molecules will be source for the attack of electrophiles, because electrophiles are the electron deficient ones. Okay, it is because of this reason, among the 3 types of the reagents, electrophiles are the preferred reagents on the phenanthrene ring system. Why substitution only? Because even after substitution of phenanthrene, the rings, they maintain the aromaticity, they preserve the aromaticity. It is because of this reason, phenanthrene, it undergoes electrophilic substitution reactions. Now coming to the mechanism involved in these electrophilic substitution reactions, it is same as that of benzene. That is electrophile formation, rate determining step where carbocation is formed, and the third step is deprotonation. All these steps you can write similar to that of benzene or naphthalene. Okay. Now coming to the point of attack here, The phenanthrene consists of 5 different hydrogens. Okay. Now the incoming electrophile, what is the preferred point of incoming electrophile? Okay. At these 5 positions is very, very important. Okay. So the preferred point of attack of electrophile on phenanthrene can be at first position. Okay, or at second position, third position, or fourth position, or it can be at ninth position. So these are the 5 different positions, 5 different hydrogens present in the structure of phenanthrene. Okay. Now how we can make out which attack is predominant? It depends on the stability of the resulting carbocation in the rate determining step. That means we have to write here 5 attacks. Okay, we have to write the rate determining step and the formation of corresponding carbocation and the possible number of resonance structures for each carbocation in all these 5 attacks. Dear students, pause this video at this particular stage, okay, and try to write the carbocation formation, that is step 2 in the electrophilic substitution reaction when it comes to the phenanthrene. Okay. Write the structure of phenanthrene, write the resulting carbocation structure in 1 attack, 2 attack, 3 attack, and 4 attack, and finally 9 attack. Okay, so these resonance structures you can draw similarly anthracene. Okay, so this was elaborately discussed in anthracene, so you can just follow that particular flow. So I hope you might have tried to a little bit. For your clarity, I am explaining here again. So here, first write the structure of phenanthrene and show all the possible attacks. Okay, 1 attack, 2 attack, 3 and 4 I have not given because you can write them similar to that of 1 and 2 attacks. You will be getting similar types of products. Because 9th attack is different, so I have shown it separately. Now let us first consider about the 1 attack. So this is the first position on phenanthrene structure. Okay, when electrophile attacks on first position, it utilizes the double bond which is present at first position. So at first position already hydrogen is there. Now electrophile makes a bond at first carbon atom by utilizing this double bond. Okay, in that case the second carbon it becomes electron deficient. Okay, keep the other double bond which is present in first aromatic ring same, and also draw the remaining 2 aromatic rings, 2 and 3 rings similarly. Okay, so we are not changing the other part of the structure. So that is how we will be getting the carbocation in 1 attack. Okay, now for this carbocation we can write one more resonance structure, because to remove the positive charge from second position, here neighboring double bond is present. Just shift this double bond, okay, to the adjacent position. So in that case, the fourth carbon, it becomes electron deficient, okay, and that's why keep a positive charge at the fourth carbon. So this is how one more resonance structure we can get for the resulting carbocation. So in this structure also, the other double bond position and other 2 rings we have drawn similarly. Don't disturb the remaining molecule. Wherever exact change is happening, make that change only. Okay, remaining structure will be drawn similarly. So here 2 resonance structures for the resulting carbocation are shown here, students. Now we can delocalize or shift the double bonds which are present in the other aromatic ring systems also to subsequently remove the positive charge. Okay, so here simply I have written as and so on. That means few more resonance structures are possible. But the thing what we have to observe here is the stability of the resulting carbocation. If you look at the carbocation structure here, wherever the substitution is happening, that is on the first ring system, there is destruction of the aromaticity. While the remaining 2 rings, they are maintaining their aromaticity. Okay. In fact, the carbocation which is formed in 1 attack is a naphthalene derivative, because this is naphthalene structure. Okay. Now this naphthalene structure is having some structural feature. That means it can be considered as naphthalene derivative. Now, once this carbocation is formed, immediately it will undergo third deprotonation step. Okay, and it gives corresponding 1 substituted phenanthrene as the product. Now coming to the 2 attack, this is the second position. Okay, when electrophile attacks at second position, it utilizes the double bond present at second position. Okay, so we have attached hydrogen. Hydrogens are already present at second carbon, and Y group, that is electrophile, is attached to the second position. Okay, so in that case, the first position it becomes electron deficient. That is why a positive charge is shown at first position. Okay, so here also few more resonance structures are possible. Okay, just shown as and so on. Okay. Now look at the structure of this molecule. Here also, wherever the substitution is happening, that is on the first aromatic ring, there is disruption of aromaticity. Okay, but with respect to other 2 rings, okay, aromaticity is maintained. And also, if you look at this structure, you can easily make out this resulting carbocation is also derivative of naphthalene. This is naphthalene structure. So it can be considered as the derivative of naphthalene. So here also, as soon as the carbocation is formed, it will undergo the third deprotonation step, and that is how we will be getting finally 2 substituted phenanthrene as the product. Now coming to the 3 and 4 attacks also you have to make, students, similar to that of 1 and 2 attacks. Okay, so in 3 and 4 attack also you will be getting carbocation which is the derivative of naphthalene. Okay, so that is why I have not shown it, okay, because I want to accommodate all these attacks in one single slide. Now coming to the ninth attack, this is the ninth position. So when electrophile attacks at ninth position, it utilizes the double bond present at ninth position. So at ninth position, we have shown hydrogen one side, Y group, that is electrophile on other side. Okay. In that case, the 10th carbon, it becomes electron deficient. That is why a positive charge is shown at 10th position. Okay. Now coming to the 1 and 3 ring systems, we are not disturbing 1 and 3 rings. Okay. So write the 1 and 3 rings double bond position same as that of the phenanthrene structure. Okay. And that is how few more resonance structures are possible even for the resulting carbocation in 9 attack also. Now, if you look at the carbocation structure in this 9th attack, okay, it consists of two isolated benzene ring systems. So 1 and 3 rings are benzenoid ring systems, okay, and that is how you can consider the carbocation resulting in 9 attack is the benzene derivative. As soon as the carbocation is formed, immediately it will undergo deprotonation step and it gives corresponding 9 substituted phenanthrene as the product. When electrophile attacks at 1, 2, 3 and 4th positions, the resulting carbocation is naphthalene derivative. In case of 9th attacks, that is when electrophile attack at 9th position, the resulting carbocation is a benzene derivative. Now, if you compare the stability of benzene versus naphthalene, benzene derivatives are more stable when compared with naphthalene. So it is because of this reason, greater stability, benzene derivative, because 9th attack resulting carbocation is a benzene derivative. So this carbocation is formed easily. So as soon as it is formed, immediately it will undergo deprotonation and it gives corresponding 9 substituted phenanthrene rapidly. So it is because of this reason, among these 5 attacks, 9 attack is the preferred point of attack in case of phenanthrene. So the same is mentioned here. In 1, 2, 3, 4 attacks, it gives carbocation having naphthalene ring, while in 9 substitution, it gives carbocation which is having 2 isolated benzene ring systems. So if you consider the stability, benzene is more stable than naphthalene. So the carbocation which is formed in the 9th attack is more stable when compared with all 4 attacks. Hence, the preferred point of electrophilic attack on phenanthrene is at 9th position. Now that you have learned that 9th position is the preferred point of attack, now let us consider a few examples for the electrophilic substitution reactions of phenanthrene. So here again phenanthrene structure is given. Okay. So the first reaction, let us consider nitration reaction. It occurs in the presence of concentrated nitric acid and concentrated sulfuric acid. So from this nitronium ion will be generated and this nitronium ion attacks at 9th position because that is the preferred point of attack. So just attach nitro group at 9th position. And that is how 9-nitrophenanthrene is formed as the product. Now the next reaction is the bromination reaction. So here phenanthrene is treated with bromine in the presence of carbon tetrachloride. So from this reagent, the positively charged bromonium ion will be generated and it attacks at 9th position. And that is how we will be getting 9-bromophenanthrene as the product. Now the third reaction is Friedel-Crafts acylation reaction, which occurs in the presence of acetyl chloride and aluminum trichloride. So from this reagent, acetyl cation will be formed as electrophile and it attacks at 9th position. Okay, it attacks at 9th position. So attach COCH3, that is acetyl group, to the 9th position. That is how it results in the formation of 9-acetyl phenanthrene. Now the fourth reaction is a formylation reaction. So here N-methyl aniline aldehyde is used in the presence of phosphorus oxychloride as the reagent. So from this reagent, formyl group, that is CHO group, will be released and this group will be attacking at 9th position. Okay, so attach CHO group to the 9th position and that is how finally 9-formylphenanthrene is formed as product. So we can write the name of this compound as 9-formylphenanthrene or phenanthrene 9-aldehyde. Both are same. I hope the electrophilic substitution reactions, particularly the point of attack in case of phenanthrene, is clear to you students. So in each of 1, 2, 3 and 4 attacks, okay, the resulting carbocation is a naphthalene derivative. When it comes to the 9th attack, the formed carbocation is the derivative of benzene. And benzene derivatives are more stable when compared with naphthalene. And that is why 9th attack is preferred when it comes to the phenanthrene. Okay, so I have discussed examples also. I hope this is clear to you. If you have any doubts related to the electrophilic substitution reactions, you can keep in the chat. So now that you have learned about electrophilic substitution reactions, the next category of reactions that I will be discussing are addition reactions, oxidation and reduction reactions. Okay. So if you are watching the replay of this particular session, then a WhatsApp group link will be available in the description of the replay. You can join in that WhatsApp group and if you have any doubts and you can clarify your doubts at later stage. Now let me share my screen to discuss about the other reactions of phenanthrene. So here two model reactions were given under addition reactions. The first reaction is addition of bromine. So even during addition also, the preferred point of attack is at 9 and 10th positions. So when phenanthrene is treated with bromine, so a mole of bromine gets attached to 9th and 10th positions. And that is how there will be formation of 9,10 dibromo dihydrophenanthrene as the product. The second addition reaction is ozonolysis. So here also the double bond present at 9 and 10th position will be affected during this ozonolysis reaction. When a mole of ozone reacts with phenanthrene, so this ozone molecule will be cyclized between 9 and 10th carbon atoms. So that is how here O3, you can see here 3 oxygen molecules are cyclized at 9 and 10th position on the phenanthrene ring system. And that is how it results in the formation of phenanthrene monoozonide. This phenanthrene monoozonide is subjected for hydrolysis so that it gives corresponding dialdehyde upon hydrolysis. Now the resulting dialdehyde, when it is subjected to oxidation in the presence of potassium permanganate, wherever aldehyde groups are there, they get converted to carboxylic group. And that is how finally diphenic acid is obtained upon this ozonolysis followed by decomposition. So ozonolysis and addition of bromine, these are the two examples under addition reactions. Now let us consider the oxidation reactions first. Phenanthrene gives different oxidative products which depends on the type of oxidizing agent used. When phenanthrene is oxidized in the presence of sodium dichromate and glacial acetic acid mixture, then the 9,10 double bond will be subjected for oxidation and there will be formation of 9,10 phenanthraquinone as the oxidative product. Now the other type of oxidation reaction is performed in the presence of peracetic acid. So this peracetic acid is a strong oxidizing agent. As a result of this strong oxidizing agent, the double bond, wherever the double bond is present, that means the second aromatic ring system will undergo cleavage and oxidation occurs with respect to the 9 and 10 carbon atoms. And that is how there will be incorporation of carboxylic groups and we get finally diphenic acid as the oxidative product. So these are the two examples of oxidation reactions of phenanthrene. Now coming to the reduction reaction, phenanthrene undergoes reduction in the presence of sodium ethanol mixture. So here also the double bond which is present at 9-10 positions will be reduced and as a result of which there will be formation of 9,10 dihydrophenanthrene as the reduced product. So these are the oxidation and reduction reactions of phenanthrene. I hope the other reactions, that is addition, oxidation and reduction reactions of phenanthrene are clear to you. So if you have any doubts related to this topic, you can keep your doubts in the chat. So we are left with only structure and uses of phenanthrene derivatives. So let us now discuss about the structure and uses of phenanthrene derivatives. Along with that, I'll be discussing about another important topic, that is diphenyl and triphenyl methane, these compound structure and uses. Okay, repeatedly this question has been asked in the previous question papers. Now let us consider the same. Let me quickly share my screen. So phenanthrene as such is not available, but phenanthrene ring system is present in some of the natural products as well as medicinal compounds. Now let us consider few examples of phenanthrene derivatives. So here I have given only two examples, students. The first example is morphine. It consists of phenanthrene ring system. So you can see the carbon skeleton. It consists of actually 5 ring systems. Only the 3 rings which are given in bold, that is highlightation, are the phenanthrene ring system. So this is one. So this is one. This is second ring system and this is the third ring system. These are part of the phenanthrene ring system. I have labeled these 3 ring systems as 1, 2, 3 ring systems. So even though it consists of 5 ring systems, 4 and 5 pyridine ring, but 1, 2, 3 rings are this combination. 1, 2, 3 ring combination is the phenanthrene ring system. It is a actually reduced phenanthrene ring system present in the structure of morphine. Morphine is an opioid analgesic agent. It is used to relieve deep pains. Now coming to the other example, it is cholesterol. So you can see here this particular carbon skeleton. This particular cholesterol also consists of 4 cyclic rings which are fused angularly. Okay. So these 1, 2, 3 rings are reduced phenanthrene ring systems. Okay. So this cholesterol is the major component of cell membranes and also it is essential to synthesize hormones, fat soluble vitamins, bile acids. So this is the importance of cholesterol. So morphine and cholesterol are the 2 examples for compounds containing phenanthrene ring system. So these are the structures of diphenyl methane and triphenyl methane. So here first structure is diphenyl methane. Methane formula, as you are aware, it is CH4. Out of the 4 hydrogens, 2 hydrogens of methane are replaced with the phenyl groups. That is why it is known as diphenyl methane. Now coming to the other structure is triphenyl methane. So here also out of the 4 hydrogens, 3 hydrogens of methane are replaced with the phenyl groups. That is why it is named as triphenyl methane. Diphenyl methane is used in perfumes and soaps manufacturing industries because of its germanium-like odor. And it is also used in making of creams and lotions. In addition to that, this diphenyl methane and its derivatives are used in the preparation of diaryl methane dyes. Now coming to the triphenyl methane, it is also used in the preparation of triaryl methane dyes. That means basically these two compounds and their derivatives, they are used in the manufacturing of corresponding dyes. So I hope the structure and uses of phenanthrene derivatives and diphenyl and triphenyl methane derivatives is also clear to you students. So I'll stop my session here because with this, the chemistry of phenanthrene is successfully completed. And by today, all the units, okay, important topics were covered, okay. So I'll just share my screen quickly to discuss about, to show some of the important questions from the phenanthrene. Meanwhile, if you have any doubts related to today's session, overall session, or any of the sessions, okay, any of the topics, overall POC-II related topics, also you can type your questions in the chat. So these are the few important questions from phenanthrene as well as diphenyl methane and triphenyl methane. So when it comes to the phenanthrene, structure and uses of phenanthrene derivatives may be asked for 2 marks, okay. And similarly, phenanthrene resonance structures, okay, Haworth synthesis and at least any 3 reactions and uses of phenanthrene derivatives may be given for 10 marks, okay. Now the other 2 small topics are also very, very important, which you may get as 2 marks questions. That is structure and uses of diphenyl methane and triphenyl methane, okay. So these questions were given for 2 marks repeatedly in the earlier question paper. So these are the few important questions when it comes to phenanthrene, diphenyl methane and triphenyl methane. So with this particular course is completed, students. Today is the last day of this particular course program. So if you are watching only this particular session and if you have missed the earlier sessions, then all the replays, 14 days replays will be available on my YouTube channel. Okay. So if you are facing challenges, any challenges in POC-II, all the examination point of view, important topics were clearly covered in my sessions. Okay. As you are aware, this session was about 15 days. So all the previous sessions are available. Replays are available. You can watch it on my YouTube channel. Okay. And in all these replays, there will be a WhatsApp group link will be available in the description of all these sessions. Okay. So if you are watching these replays, then you can join in that WhatsApp group and you can clarify your doubts at later stage. So if you have any doubts related to POC-II course contents, okay, if it is small doubt also, there will be a WhatsApp group link will be available in all these replays description. You can join in that WhatsApp group and you can clarify your doubts at any point of time. Thank you so much, students, and thank you so much for your support. You have shown consistency throughout these 15 days. So if you have any doubts, even in the future semester, that is POC-III also, if you need any assistance for POC-III also, I am offering a online course which you can learn at your own pace at very, very affordable price. Okay, so if you want to know the details or if you want any other type of support when it comes to the pharmaceutical organic chemistry, then you can contact me. My mail ID is also provided in the description. As I mentioned previously, on the first day of this course itself, set a goal. That is very, very important, students. Okay, so without goal, it is difficult to maintain the consistency. So whether your goal in this particular semester is to clear POC-II subject, okay, or if you are already comfortable with the fundamentals, then your goal is to achieve B grade, okay, or A grade or O grade. Okay, so set your goal first. Okay, accordingly you prepare. Okay, and this, whatever the course, that 15 days course that I have taken so far, is meant for all types of students. If you are a student whose goal is to just clear the subject, that means if you want to get only pass mark, you don't want to work hard after this particular subject, just you want to get the pass mark, okay, then also you need to have separate strategy. Okay, similarly, if you are a B grade student, okay, but want to achieve for the aim for the higher grades, that is A grade and O grade, then you have to implement separate strategies. Okay, so if you want that customized guidance or mentorship, in that case also you can contact me. My mail ID will be given in the description of this particular video. Okay, if you are attending the live session, or even for the replays also, in the description you can find my mail ID. Okay, so whatever maybe your doubts and what type of support that you need from me, you can send me mail, okay, with all the details, then we'll work out. If you write what is your goal and what is expected from me, then definitely I'll support you. We will work it on to achieve your goals. Okay, so don't hesitate to get the help from me, to get the support from me. So I'll be definitely answer your mails. Okay, so thank you so much for your consistency and wish you all the best for your final examinations.